Here it is. What atoms could that be right there? What atoms could that be? Kinds of elements. Could be nitrogen, phosphorus. All right, very good. Again, Lewis dot structures are helpful not for ionic compounds, but what kind of compounds did we say? Molecular compounds. And so it's mostly dealing with just those nonmetals up there in that corner. Okay, so that's kind of nice because it's very limited in the number of elements that we're dealing with. And we introduced to you guys a list of steps here. What's going on? F8. A list of steps to draw Lewis dot structures. A list of steps to draw Lewis dot structures. Okay? Yeah. Okay. I think I have some more here. Does anybody remember? What's the first thing we do? Anybody else need slides? We have to identify the central atom, right? The central atom. And in this, let me pass that back there. This class, the central atom will generally be the one that there's the only one of, right? Only one of them. So that's a nice, easy way for us to identify the central atom. After we identify the central atom, we draw a skeleton structure about it. Okay? So this is the compound that we're going to draw for practice here. Okay? Actually, no, we'll do PH3. Okay? So, what would our central atom be, do you think? Phosphorus. So we draw the phosphorus, and then what do? Yeah, we draw bonds to the to the other three elements in the compound, or whatever the other elements are in the compound. Okay? So I call this kind of like the skeleton of our molecule to start off with. The next thing we do, does anybody remember what's next? We only did it once, so you might not remember. Okay, we count up the valence electrons that are brought to this party. And remember, we use the analogy of a party, right? Like all of these atoms are going to a party, and what's the thing you got to bring to a party? Food. You got to bring food to a party, right? You got to bring snacks. Everybody brings a certain number of snacks. Phosphorus brought how many snacks to this party? 5. That's valence electrons, right? And remember, the valence electrons look something like that, right? So phosphorus brought 5. Each hydrogen brings 1. So that's another 3, a total of 8 valence electrons brought to the party. Okay? What is that there? Is that...
Oh, it's, you don't have to keep doing it. I was before class. It's a petition.
Okay, that's fine. She thought it was attendance, right?
No, it's not.
But you can sign it. Tell us about it. Tell us about it so everybody knows what it is.
It's for my biology class. I get extra credit if you sign it right away.
Get rid of Dr. Weeks? Is that what it's about?
But it's a petition to like decrease the use of single plastics on campus.
Oh, okay, great. Okay, so we got 5 here for the number of electrons that phosphorus brought. Does everybody know how we knew phosphorus had 5 valence electrons? Okay, nobody needs to talk about that? All right, so 8 valence electrons. Now, all these 8 valence electrons need to be represented in this compound here. Did somebody raise their hand when I asked if anybody wants to talk about how we knew phosphorus had 5? Okay, so phosphorus is in the 5th row if you count it like this, right? Where's my stick? If you count 5th column, sorry, if you count columns like this. 1, 2, 3, 4, 5, 6, 7, 8. So phosphorus being in the 5th row, that means it has 5 valence electrons. 5 valence electrons. And valence electrons are placed around the element to visually kind of identify how phosphorus would like to interact with other elements by visualizing 4 regions, and those 4 regions are cut into 2 spots each, and so we can just distribute the 5, whoops, that's 6. You can distribute the 5 as far distributed as possible. You would never see something like this, right? You want to fill up every region before a second one's filled up, okay? So that's how we knew that there were 5 electrons, and that's how we remember how to draw a Lewis dot structure. Okay, after we've identified all the electrons that are brought to this molecular party, then we count how many electrons we already have represented. That bond, what does that bond represent? Like oxygen that has 6 valence electrons interacting with hydrogen that has 1 valence electron. See, there's a space here for that valence electron to interact with the missing space there, right? And the result is oxygen, 1, 2, 3, 4, 5. Hydrogen comes close and makes that what do we call that when electrons begin to share between 2 atoms? A bond. Very good. And we can also display the bond with a little line. So each line represents 2 electrons. Is everybody comfortable with that statement there? Okay, so phosphorus, hydrogen, hydrogen. We're going to put 8 electrons on this molecule. The 8, again, is the sum of all the valence electrons that were brought by the different elements to this party. How many are already displayed based on our drawing? 6. There's already 6 out there. So I have only 2 left. 2 left. Now, I put these 2 on elements in my molecule in an effort to make sure everybody has access to the number of electrons they need to fill their valence, their outer shell, and everybody wants to have the number of electrons they brought to the party right around them. Okay? So, phosphorus has access right now to how many electrons? 6. Right now it just has these 2, 4, 6. But it needs to have access to 8. All the elements want access to 8. All the nonmetals want access to 8. Except for, what's the exception? Hydrogen. Right? It only wants access to 2. Okay? So, phosphorus has access to 6. It's going to need 2 more. So I'm going to put 2 electrons on there. And that actually makes my electrons gone. I'm out of electrons. Is that okay? Right now, phosphorus has access to how many electrons? 8. Has access to 8 electrons. How many electrons does it have right around it? That means 1, 2, 3, 4, 5. Because remember, this bond is really a representation of 2 electrons. 1 right around phosphorus, 1 right around hydrogen. So phosphorus has 5 electrons right around it. It brought 5 electrons to the party. It's content with this interaction, right? Hydrogen. How many electrons did it bring to the party? 1. How many does it have right around it? 2. There's the hydrogen, 1, 2. That's how many it wants, so it's content as well. And good thing, because we're out of electrons. So that is the structure of phosphorus trihydrogen or phosphorus hydride. Okay? Oh no, the car place is calling. That's all right, they can wait. Okay, so let's have you guys try to draw a molecule now. Oh well, let's talk actually before we send you free to draw your own molecule. Let's talk about what this means. We need to recognize how many regions of electron density are around our central atom. How many regions of electron density are around our central atom? We have one region here which is called a bonding region, a second bonding region, a third bonding region, and one non-bonding region. So a total of how many regions? 4. 4 regions. And what did we say? Central atom with 4 things on it, right? What is the angle that exists between any one of these? So this should be more like that. There we go. What's the angle that exists between this phosphorus hydrogen and this phosphorus hydrogen bond. What is that angle right there? 109.5. 109.5. Now, if you were out for some classes and you don't know that number, then there's no intuition that'll help you know that number. That's just what happens if you have something in a central region with 4 other things attached to it, and they all spread out the best they can, right? The result is an angle of 109.5. If I have 3 things attached to one central atom, what's that angle? Three things attached to one central atom. What does it look like? Any ideas? Did I tell you the story of the football coach? It's 120. Right, I didn't tell you the joke about the football coach. It's not a joke, it's a true story, but... No? The football coach, new football coach, says, okay, I'm here to change things around. We're going to turn this team around 360 degrees. Right? What's that mean? This is, full circle. Coming right back to where we were, right? Does that make sense? So if you want to be a football coach and say you're going to change things, you got to say, we're going to turn this team around 180 degrees. Anybody want to practice it? No. Who wants to practice saying, we're going to turn this team around 180 degrees? Don't we have some, exercise science majors in here? Nobody wants to practice? Okay, so 180 degrees. If we're just going a third of the way around the circle, then what is it? That's 120. 360 divided by 3, right. 120 degrees. All right, so these are numbers that we're going to want to increase our understanding of or renew it. But this one is a new one. 4 regions around a central atom, and that's 109.5 degrees. And this is 4 regions. 3 of them are bonding, and 1 is non-bonding. All right? Okay, very good. So now I will give you your molecule. You ready for your molecule? It's a good one. It's a good one. Okay, here it is. What is the angle between the selenium fluoride bonds in SEF2? Okay, so we're drawing SEF2, and we want to know the angle between those bonds. Okay, I'll give you a little push start. What's the central atom? Selenium. Then we draw our skeleton, right? And then we draw or count up electrons brought to the party. Then we try to distribute electrons in such a way that everybody has, there's no hydrogens here, so everybody's going to have 8. 8 available to them, and the number they brought right around them. Okay? Yeah. Slides. It's chapter 9 still. It's not. Okay. The roll going around somewhere? Did I hand out a roll? Okay. Okay. Everybody get it? Looks like everybody got it, right? So today at 4 p.m. there's something going on in 134. 134, a gentleman's coming who's alumni who works at a scientific company in Illinois or Ohio, something like that. Where is it? Anyways, he's here to see if he can recruit people to be interns back there. Why isn't this working? I think so. Just for a summer. So that's it for today. And I'll give you guys 3 points extra credit if you guys want to go listen to that. That's a quiz, right?
Where's that?
134. So that's kind of towards the security office if you go this way, right? Right by my office. I don't know if you guys know where my office is, but. Are you guys done already, or was it not that hard? Wait a second. Oh, okay, that's the problem. All right. All right, should we talk about it? Who needs more time? Raise your hand if you want more time. Yeah? A little more time? No, somebody raise their hand? Okay. All right. Well, we drew the central atom. Selenium, what's next? All right, bonds to what? Fluorine, right? And we always try to spread those out as far as possible, okay? All right. Next, what's the step? What are we supposed to do next? That's right, we count up valence electrons. How many valence electrons total? All right, selenium brought 6. Oh, did I say SEF2? Okay, all right. Will this work? I don't know if this will work. It's supposed to be SEF3. Wait, is that? No, that's right, No, is that right? Oh yeah, that's right, Sorry, this is right. Okay, SEF2. So 6 here, and then what? 7 times 2, right? So 14. So 20 electrons. Okay, 20 electrons. And how many do we have up here already represented by the bonds? 4. All right, 4 electrons. Now what do we got to do? We got 16 more to place. Okay, so where do they go? It's good to start with the central atom. How many more electrons do we need there? 4. 4 more electrons, and that comes in 2 pairs like that. Okay, so there's 4 electrons gone, and then we got 12 valence electrons left. And now selenium has access to how many electrons? Access to 8. 1, 2, 3, 4, 5, 6, 7, 8. How many electrons does it have right around it? 6. 1, 2, 3, 4, 5, 6. Okay? All right, we have 12 electrons. How about fluorine? Is it done? Is it happy? It needs how many more? 6. In fact, each of one of these is going to need 6 electrons. Okay, but that uses up all our 12, right? Is fluorines, now if the formal charge on fluorine, okay, now what the formal charge means, whoops, where are we at here? The formal charge is what we call the number of electrons that it brought to the party minus the number that it has right around it. All right? So, again, we talked about elements bringing electrons, bringing snacks, but wanting to have access to the same number of snacks that it brought, right? So fluorine brought 7. 7 minus, how many electrons are right around fluorine there? 1, 2, 3, 4, 5, 6, 7. So we have number of electrons that we have access to and number of electrons directly around. All right? So listen closely to those differences, right? If we have access to them, that means that it could be the ones that are directly around, but also any ones that are in bonds. Okay? So here we have access, right around us, 7. And we subtract the number of electrons that we brought to the party. Oh, no, sorry, other way around. This is how many we brought. We subtract how many we have right around us. So fluorine brought 7, and it has 7. So we say that the formal charge on fluorine is 0. Okay? So we calculate a formal charge on the individual atoms. Can you calculate the formal charge on selenium there? How many electrons did it bring to the party? 6. How many does it have right around it? 6. So there's no formal charge on selenium there. All right, so what do you think? What is the angle between the selenium-fluorine bonds in this compound? What's the angle? 109.5? No, what did you say? 180. Oh, that's close. So what we have to do is identify the regions of electron density around the central atom. Okay? What are the regions here? Let me redraw it without those circles. Okay, how many regions of electron density are around the central atom? 4. 1 here, 1 here, 1 there, and 1 there. Central atom with 4 things around it. What did we say that angle is? 109.5. 109.5. So if this is our selenium, this would be one fluorine, this could be another fluorine, this would be a lone pair of electrons, and that would be a lone pair of electrons back in the back. They have to be smaller because they're going back the other way. Okay? So we look at how many regions of electron density there are, and then that tells us about the shape of that compound. Okay, very good. So, how about this one? Carbon dioxide. Carbon dioxide. You guys want to take a stab at that one and see what happens? Or actually, maybe we should just do it together. Let's do it together. Central atom, carbon. So you can draw a skeleton with the oxygens on the outside. All right, and the question here would be, what's the angle between the oxygens and the carbon-oxygen? What's the angle between the carbon-oxygen bonds, the 2 carbon-oxygen bonds? Okay? Carbon, oxygen. This is just our skeleton. We draw it to start off with, right? Number of electrons in the party. 16? Let's see. Oxygen brought 6 each. That's 12. 13, 14, 15, 16. Is that true? 16. How many do we have up here so far? 4. So we have 12 more to distribute. Okay, where are we going to distribute them? Central atom. Good. So, looks like we need 4 more. Is that true? Huh?
Would it matter in this case because it's central atom?
Would it matter what? Did I do that right? 16, 4, 12 minus 4.
Yeah, technically, just because of the amount of valence electrons that carbon has, that's why they're saying 1 more.
Oh, I see. I see.
But we can do it 2 just because they're.
Well, carbon dioxide is an example of a sneaky molecule to draw. But we find ourselves in that scenario. Because if we just draw 2, right, then carbon doesn't have enough electron density around it because it's supposed to have access to how many? 8. But if we draw 4 on there, now carbon has too many electrons right around it. Right? It's only supposed to have 4 right around it. Right now it has 6. So yes, we see that there's some issues. And you can address these issues up front or at the end. As long as you're aware of them, then that's fine. Let's leave it like this for a little bit and then see what else has to happen. So I put those 4 electrons on. I need 8 more electrons. This oxygen, what's wrong with it right now? Needs more electrons, right? Needs up to, we could have 6. 1, 2, 3, 4, 5, 6. So then that would leave us 2 electrons. And now we can see that there's further problems because we're out of electrons, right? We're out of electrons. So what do we do in this sort of a scenario? We know that carbon has too much electron density. How can we tell that? How can we tell that carbon has too much electron density? It only brought 4 to the party. 4 minus, how many does it have around it? 6. So right now it has a -2, and what was the special name for that? Formal charge. A formal charge of -2. Okay? So we need less electron density. A minus charge on that atom, we need less electron density. So what I'm going to do is I'm going to take these electrons and move them over to this region where I know I need more electron density. Okay? So carbon. And I'm going to get a double bond there. And that's what my molecule looks like right now. Okay, we're still not quite there, are we? What do we need to do now? Who needs more electron density? The oxygen on the right. And if we were to do formal charges right now, the formal charge here is what? 1, 2, 3, 4, 5. It has right around it. How many did it bring? 4 minus the 5 that it has around it. It's a -1. So right now this has a -1 formal charge. Is there a formal charge here? Oxygen brought how many electrons to the party? 6 minus, how many does it have right around it right now? 7. So it also has a -1 formal charge. So we got too much electron density on this side of the compound, right? So maybe we take these electrons and put them over there as lone pair electrons. What will that do? That'll get us this. Right? We're getting closer to something. What's wrong? Anything wrong? Are we all okay now? Carbon still has too much electron density. Who's missing electron density now? This oxygen only has access to 1, 2, 3, 4, 6, 7 electrons. 1, 2, 3, 4, 5, 6. Sorry, 6 electrons. And it only has 5 right around it, and it wants to have 6. So what does it look like we need to do? Yeah, move this electron over to here, those electrons over there. Okay, this oxygen, what's the formal charge on this oxygen? 0. And that oxygen's in the same boat, so same formal charge. How about here? Carbon, does it have a 0 formal charge? It does. So that's how you know when you got a good compound, right? All the elements have formal charge of 0. Okay, I'm going to draw these double bonds here a little bit closer together. How many regions of electron density are around? Because the question that we were talking about is what is the angle between the carbon-oxygen bonds? How many regions of electron density are around that central atom? Just 2. This double bond counts as 1, and this double bond counts as 1. Okay? If I have a central atom with 2 regions of electron density around it, what is the angle going to be there? That's 180 degrees. Got it? Okay. Let's see what other kinds of things we want to practice. Okay. Let's see if we can get this video to work. This video is cool. Do you guys remember this guy? Bill Nye. No. It's almost. Almost. Who is this guy?
Promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now,
Okay. I'm going to plug this in so you can hear a little bit better. What was he just doing? Sucking helium. That's right. Let's go suck it, man. Okay. So, oh, what happened? Got to turn up the volume here. I'm going to turn that off. The volume. Hopefully this works. Let's try again. Okay, ready? Okay.
Promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
the simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that. And then this gets really low, and somehow I'm still funny. It's scientific.
Isn't that crazy? So we got these gas, sulfur hexafluoride there, that's much more dense than air, like helium is less dense than air. And so we have some other examples here of people using it for, or doing different little things on it. Is that working? What's going on? Oh, this one doesn't want to work. Let's see if it'll work. Oop. This one is interesting because they show it in a plexiglass box. They fill it up with the sulfur hexafluoride, and because it's more dense, it acts like a box full of water. So you can put stuff on top of it and have it float, right, on top of it. So it is like a fluid. It is a fluid, right? But it's gaseous and not a liquid. Anyway, if we look at the compound SF6, our central atom would be sulfur, 1, 2, 3, 4, 5, 6, with 6 fluorines, right? And we would think maybe right off the bat that this is a problem initially, right? Because sulfur, our central atom, has way too much electron density around it, right? This is a different class of compounds that can exist because sulfur is in the third, n equals 3, third row or lower. Once you get down to the third row, your outer shell electrons have d orbitals. So you can get sharing not just through your s and your p orbitals, but also through your d orbitals, and therefore you can have more than just 4 regions of electron density. Okay? So, you would draw it the same way. Draw your skeleton, count up electrons. Sulfur brought 6. 6 fluorines, 6 times 7, that's 42. Total of 48 electrons. Right now I have how many electrons on the board? 12 minus 12, that gives me 36. All right, who needs more electron density? The fluorines do, each one needs 6. So that's where our 36 electrons are going to go. Okay, so following the same pattern, and that's our final structure. Let's see what the formal charge is on the sulfur. What's the formal charge on the sulfur? The formal charge is identified by looking at how many electrons it brought, minus how many are right around it? 6. So the formal charge is 0. Okay? So the formal charge on this is 0, and all these fluorines, 0 as well. Now the shape of this thing, 6 regions of electron density. What would happen if I had a central thing with 6 regions of electron density? Well, it would be like a coordinate axis, because there's 1, 2, 3, 4, 5, 6 regions around a central atom. Can you guys see that? So this would be 1 fluorine, 2nd fluorine, 3rd, 4th, 5th, 6th. Okay? Anybody want to guess what the name of that shape is? Well, the shape's name has to do with what it would look like if it was a dice and you rolled it. How many sides would it have if it was a dice? Can you see? These 4 here would make a 4-sided pyramid on top. Can you see it? And the bottom ones would also make a what? 4-sided pyramid on the bottom. Total of how many sides?
6.
Let's try to draw this top again. Here's the top. Here's the base. It's a square base. 1, 2, 3, 4. So how many sides? 4. This is a pyramid with 1, 2, 3, 4 sides. There's the base. But this is going to also have another pyramid on the bottom that has how many sides? 4. So 8 sides altogether. So it's called octahedral. Hedral meaning sided. Octahedral. Okay? So you're not going to find information about the names of these shapes in Chapter 9. It's more of a Chapter 10 thing. But we're here, we're drawing these structures, and so we're trying to roll it all together to collect as much information as possible. Okay, so we want to draw some crazy structures. XeO4F4. XeOF4. Now, here's a hint on this one. Only atoms that are 3rd row or lower can have more than 8 electrons available to it. We call this, when sulfur has so many electrons around it, we call it an expanded octet. Expanded octet. Okay? So looking at that top one there, it might be difficult to identify what the central atom is. So talk to your neighbors about how you might be able to identify what the central atom is. Only 5 minutes left.